tout le monde. On a une autre conférence palpitante aujourd'hui. Cette fois-ci, c'est professeur Alberto TESTOLIN de l'Université de Padua. Un instant, je cherche la carte où j'ai mis. Oui, voilà. Sa maîtrise et son doctorat est sa maîtrise est en informatique, son doctorat est en sciences psychologiques. Il est vraiment interdisciplinaire. Il est professeur assistant à l'Université de Padua actuellement, dans le département de génie de l'information ainsi que le département de la psychologie générale. Il s'intéresse à l'intelligence artificielle, à l'apprentissage automatique et aux neurosciences cognitives. Ses recherches portent sur la théorie de l'apprentissage statistique, le codage prédictif dont on a parlé hier soir dans l'intervention de Giuntani sur la robotique. Donc, le codage prédictif, la perception sensorielle, la modélisation cognitive et les applications de l'apprentissage profond au traitement et à l'optimisation du signal. Il est membre actif du groupe de travail du IEEE sur l'apprentissage en profondeur, deep learning, et sa présentation sera sur l'acquisition des concepts mathématiques. For the English speakers, I'm not going to repeat all of the biography, which is already available anyway. Professor TESTOLIN is at the University of Padua. He's truly interdisciplinary, and he's going to be speaking on models for the acquisition of mathematical concepts. Professor TESTOLIN.
So thanks a lot, Stephen. I'm really honored to be invited here to give a talk. I was really excited when I received your invitation because the symbol grounding problem is something that is very close and dear to my heart and my research interests. So I hope to entertain you with some exciting research directions.
And one little note I can't resist saying, your colleague Maria Felicita has just joined us, and I'm very happy that you're there.
Ciao, buongiorno.
Go ahead.
Okay, so let me share my screen. Can you see it?
Yes.
Okay. So as you can already see, the title of my topic is about the challenge of modeling the acquisition of mathematical concepts. So I'm afraid I will not give you so many answers, but maybe I will mostly raise questions about this field, which I think is still being explored. As an outline, I will first start by discussing the topic of numerosity perception. So numerosity is something that is different from a number, from exact number, and I will first introduce you to this distinction. And then I will tell you about the empirical literature that has been tried to test and measure numerosity perception. And also I will try to convince you why this could be relevant and worth studying. I will then briefly mention the issue of continuous magnitudes, because you have been hearing something related in the talk of Tali Leibovich, and I think this is a very important and contemporary research topic in this field. And then I will start to introduce you to some computational modeling work that me and other colleagues have been doing lately about this field. So the question is, can machines, and actually deep networks, so we are mostly interested in connectionist models, learn to process visual numerosity? And apparently the answer seems to be yes. But then I will move to a more challenging topic. So how can we switch from an approximate to an exact system of numbers, something that is quite symbolic in nature? And so the question is then, can machines or deep networks learn to do math? And this turns out to be a much more challenging question. So I will finish my talk by pointing out some research directions. So number versus numerosity. Actually, numerosity is something that is approximate, and it's also immediate. Sometimes people call this number sense, because you can establish the numerosity of a visual set, for example, of objects in an image, without counting. So something that you can do very fast with some approximation. It's approximate at least for numbers greater than 4. When you have a few objects in the scene, you may be able to give an exact guess of the numerosity faster without counting. So let me give you an example. You see a bunch of apples disappearing, and then I ask you how many apples were there. So I cannot easily ask for a poll, but I can tell you the answer is 18. Now let me ask you another one. Just give a very fast look at this scene, and then I will ask you how many people were there. So the correct answer is 60. And the final one, try to give an estimate of the number of sheep in this field. And of course, I don't let you count. And in this case, the answer is 107, more or less, because I was not really sure how to count some overlapping animals. So this is just to show you the complexity of this kind of task, especially if the visual scene is quite large and you have many objects. It's very challenging to give accurate estimates of the number of objects. And you can also see that the result, the accuracy, depends on the size of the objects, on the way they are spread around the visual scene, how dense they are, how overlapping they are. Maybe you can find some proxies, so you can just try to establish the density and do some heuristics to infer the numerosity, which is something that Tali was mentioning in her talk. However, it's quite unknown which are the exact mechanisms allowing humans and also other animals to perform this kind of numerosity estimation tasks. So how do we empirically test numerosity perception? You can set up a comparison task or a discrimination task. So you have two visual scenes and the subject is required to establish which one has more. Of course, the closer the numbers, the numerosities, the hardest is to give a correct answer. Or you can have a match to sample tasks. So you have a sample numerosity, then you have some delay, and then you have another set of items which is matching the number or no, and you have to establish if this contains the same numerosity of the sample image. Or you can work with the habituation paradigms. This is especially useful for children and infant studies because you don't need to give an overt, an explicit answer. You may be habituated to a series of displays with a fixed numerosity, and then during the testing, you can have a display with the same number, numerosity, or a different numerosity. And if looking time or a surprise is something that can tell you whether you are perceiving the change in this visual feature. You can be asked to do estimation, so you only have one image and you have to name the number that you guess corresponds to the numerosity, or to produce it by, for example, creating a new image with the same number of dots. This is very used in animal studies, for example, in rodent studies, where the animal is asked to reproduce the number of lever presses that have been shown during the testing phase. Or finally, another interesting task is that of adaptation. So let me give you this little experiment. Please fixate on the central red dot. Don't move your eyes. And keep your eyes fixed on the dot for a few seconds. Okay, so now we are letting our visual system to adapt to the features of the stimulus on the left and the stimulus on the right. Then I abruptly change the displays and I ask you to say which of the two images had the largest number. And my guess is that you will say the one on the right. Okay. But if we look carefully, they are exactly the same image. So it happens that you may get habituated to numerosity, and so you may underestimate one image over the other. So this is just a few examples of how you can empirically test numerosity perception. Then if we want to measure numerosity perception, we need to do some psychophysical studies and psychophysical measures. So for example, the most famous one is the so-called Weber fraction. Basically, you can plot the percentage of larger responses in a discrimination task or in a comparison task by putting as a x-axis the numerical ratio. So if the ratio between the two numerosities that needs to be compared is close to 1, the subject will be almost at chance level in activating the correct response. However, if one image has much more items compared to the other one, then you will accurately, most of the time, say that is larger. And similarly, if the other one is smaller, you will most of the time say that is smaller. Okay, so this psychometric function can be used to estimate the number acuity of a participant in a numerosity perception task. So there are many theories about how this kind of behavioral signature could raise due to some neural encoding of numerosity. So one of the most popular analytical models for explaining this pattern of behavior is that we organize numerosities according to something like a number line. So every numerosity is represented by a Gaussian activation curve over numbers. Okay, so the mean of each Gaussian corresponds to the true numerosity, but then the variability of these curves increases with numerosity. So this is a linear model with scalar variability. Or alternatively, another popular model is a logarithmic model with fixed variability. So the idea that these distributions have all the same variance, however, the means are displaced according to a logarithmic compression. So this can be considered equivalent in some respects, but they have some subtle differences. But the take-home message is that you can use this approach to calculate the so-called Weber fraction, which is the standard deviation of the estimated Gaussian distributions in this logarithmic model. So basically, the more your distributions overlap, the worse it will be. Your numerical acuity and your Weber fraction will be higher. Okay, so now why should we care about all these numerosity perception studies? Well, one prominent view is that because the Weber fraction, so the number acuity, predicts later mathematical learning. So this view was put forward mostly by people like Brian Butterworth or Stanislas Dehaene, and it was further promoted by some research that showed that individual differences in non-verbal number acuity, so numerosity perception, actually correlate with later mathematical achievement. So this was work mostly done by Alberta and colleagues, but then it was replicated by other scientists. However, as maybe Tali pointed out, successive studies failed to replicate this finding. And actually, it seems that maybe later mathematical achievement can also be predicted by other factors, like cognitive control, inhibitory capabilities, or maybe the ability to estimate other quantities or to do symbolic number comparison, and so on and so forth. So there is a little bit of controversy into this topic. So I will also tell you that maybe you just care about this because you are interested in understanding the computational basis of human perceptual and cognitive abilities. So if you are not happy with this first motivation, I think this is still a quite reasonable one to further explore this topic. Now, some people have been proposing that numerosity perception is a widespread ability because even children, actually even infants to some respect, can succeed in this kind of numerosity comparison tasks. Even monkeys, so other primates, can do the same. But even dogs. Studies have been done with rodents, with dolphins, with lions, so many different kind of mammals, and even birds or insects, invertebrates, fish. So really, it seems that this is a widespread perceptual ability. So of course, the natural conclusion is that probably also neural networks, like deep networks, can do something similar. So this was the research direction that I pursued in my recent studies. So if number sense is a product of evolution, this may be explained because it has been evolved to enhance the fitness of the individuals. So for example, if you take a group of chimpanzees, they tend to fight against another group of chimpanzees only if the numerical ratio is at least 3/2 in their favor. So it seems that they can do some kind of quantitative reasoning to establish whether it is worth taking the risk or not. Or similarly, maybe if you are a fish, you want to join the larger group of conspecifics, so you want to estimate which group has more fish. Or if you are a predator, maybe you want to jump into the nest with a larger number of eggs, and so on and so forth. So people trying to sustain this claim of innatism for numerosity perception are building on these kind of examples to convince you that probably it is something that has been phylogenetically evolved. However, we recently questioned this idea because maybe you can show that numerosity perception can emerge from learning processes. So an alternative view argues that numerosity may simply be a relevant feature of our environment, visual environment, maybe in particular, if you are testing visual numerosity perception, which can be extracted along many other features by some neural networks that are learning the statistical structure of the environment. So this is the tradition of connectionism, the idea that cognition and perception emerge from the nonlinear distributed dynamics of neural networks, and that knowledge is somehow implicitly stored in the connection weights, which are gradually changed according to some objective function. So nowadays, we don't say connectionism no more, we rather say deep learning, but the idea is the same. We are now using more advanced architecture, so we are now building neural networks with an increasingly complicated set of representations organized hierarchically. But still, learning tries to discover the hidden factors of variation in the sensory data. So the question is, can deep networks learn to estimate numerosity by just trying to factorize it from some data distribution? So let me open a little parenthesis on the issue of continuous magnitudes, because this was mentioned by Tali in her own seminar, and I think it's a very important point. So numerosity, of course, is not the only magnitude that you can extract from numerical stimuli, so from images, for example. Your visual system could also extract the total area, the total luminance of the display, or the total perimeter, or the individual item size, the individual perimeter, the field area, which Tali called convex hull, or the density, so how close different objects are between each other. So these are all perceptual features, which is reasonable to think that our visual system can also extract. So for example, if you ask a children to choose between these two displays, maybe he will go for this one, even if it has a smaller number of objects. It's the area now that is predominating in establishing which should be the answer, the reaction to this stimulation. So I'm totally in agreement with Tali that maybe other continuous non-numerical magnitudes could be extracted by our visual system. But the question is numerosity something separate from these magnitudes, or is it a product of these magnitudes, as Tali and others are proposing? So in the literature, in the recent literature, many people have been questioning the construct of number sense and numerosity, because they say that probably numerosity can be derived from non-numerical continuous magnitudes. Okay, so Tita Gebuis, Bert Reinvoyer, Tyler Leibovich, and others have been pushing on this direction. And actually, as I told you, they even found that individual differences in inhibitory control, not in number sense, correlate with mathematics achievement. So there's a lot of controversy in the literature, and this is why I think it is very useful to try to build computational models of this kind of perceptual domain. So the question is now, can machines, in particular connectionist models, deep networks, learn to process numerosity. So I don't want to spend so much words in introducing you to deep learning, because I think that most of you are familiar with the general ideas, but I want to mention that I will focus initially on unsupervised deep learning. So what is called hierarchical generative models like deep belief networks, variational autoencoders, generative adversarial networks. What happens in these models is that we have some sensory stimulation, and then we have many layers of representation. And basically, we are trying to establish the probability of some features, some activations, given the evidence provided by the sensory signal, okay? And we can do this hierarchically. So deep networks can learn hypothesis over hypothesis, thus creating increasingly more complex representations of the data. This can happen in a totally unsupervised way by just observing the statistics of the environment. And somebody says that deep layers builds abstract representations by discovering invariant features from the data. Now, what does it mean to be abstract is a matter of course, discussion. The question in this case is, can we build representations that are specifically representing numerosity rather than other features from the sensory stimulus? And of course, once that we have a deep network that has built some abstract representations of the data, we can probe its knowledge by also using some supervised tasks. So for example, we can stack a readout classifier on top of these representations and ask the deep network to perform a numerical comparison task, for example. So in other visual domains, like for example, face perception, people have been showing that a deep network can learn a set of increasingly more complicated and more sophisticated visual features from the data by building a hierarchy of visual concepts. And this was kind of done also for numerosity perception. So this was one of the earlier computational works with deep learning and numerosity perception, where Stoyanov and Zorzi have shown that if you show to a very simple deep belief network composed by two layers of hidden neurons, a data set containing a variety of images, so each square here represents an image that was given as input to the deep network, and you vary the number of items. So numerosity becomes a latent factor of variation in this data set. Of course, you also vary the item size, the total amount of surface covered, the positions of the objects, and so on and so forth, but also you vary numerosity. Then maybe you can see if the neural network is able to disentangle the numerosity feature from other visual features. And you can even stack on top of it a classifier, maybe a simple linear classifier, which is trying to perform a numerosity comparison task. So in particular, in the original model, Stoyanov and Zorzi were asking the deep network, following unsupervised learning, they were stacking this classifier to learn this comparison task, whether you have to establish if the input numerosity is larger than 8, or in another set of simulations, larger than 16. So you have an internal reference number, and the task is to establish whether the input has more or less items compared to the reference number.
I have a question, Alberto.
Yes, please.
Why did Marco and his collaborator look at a relative task rather than an absolute task at the top of the hierarchy?
So like asking to give the exact numerosity, yeah, like an estimate of the numerosity. Yes. So this is a good question. So I think they could have done that. I think that could have been just a slightly more challenging task, because this comparison task is a binary classification. So you just have to say left or right, yes or no, while giving an absolute judgment requires as many categories as the number of numerosities in your data set. So if your images contains up to 30 objects, then you need to activate 30 separate categories. We have been doing this later, so I will not show you results on this, but there is some literature about deep learning models for estimation, and the result is quite consistent. So also in that case, you can estimate the Weber fraction by computing the coefficient of variation in the Gaussian distributions corresponding to each numerosity.
Thank you.
That's a very good question. Thank you. So this is the basic behavioral result. So similarly to the human psychometric function, also for deep networks, you have this effect whether as the number comes close to the ratio of 1, so if you show, for example, an image with 8 objects and the task is to establish whether it is greater than 8, then the response is at chance level. However, as the ratio increases or decreases, then the model can get more confident and be more precise in the discrimination. So also in this case, you have a psychometric function like this, and you can estimate the Weber fraction of the model, which is very similar to the Weber fraction of human adults. So this was the first evidence that the model was indeed trying to estimate the numerosity of the input image. You can even try to look into these hidden units activations to try to understand how the deep network is organizing internally in order to create numerosity representations. So in the first hidden layer, these are the receptive fields of different hidden neurons. So you see these are like on-center, off-center detectors. So this is a very basic form of visual spatial processing that is basically detecting the borders of the objects and finding out where is the actual activation of the pixels in the input image. But then if you move into the second hidden layer, you see something more interesting to emerge. So there are some neurons whose population activity strongly correlates with numerosity. And even if you change the cumulative area of the objects in the image, you can still see this robust behavior, whether the population activity decreases as the numerosity in the display increases. So this is a monotonic encoding of numerosity. But we find even other kind of activation profiles where you see some neurons specifically tuned for some numbers. For example, this neuron here is mostly firing for the number 4. So it's being maximally activated when you have 4 items in the image. Okay? These activation profiles are a bit noisy, so I should first acknowledge this. Indeed, the encoding appears to be quite distributed. So we have some numerosity specific tuning function, but I think I will be prudent in claiming that these are number neurons, okay? However, other people like Andreas Nieder have been recently claiming that you can, in fact, discover number detectors in deep networks. So neurons that are specifically tuned to particular numbers. Now, I don't want to open a big parenthesis here. I think the methodology of these kind of studies may have some weaknesses. So I don't fully buy this idea that we have number neurons in the brain or even in deep networks. However, this is another evidence suggesting that the deep network can in fact learn to estimate numerosity in a quite interesting encoding format. So why am I puzzled a little bit by this methodology? Because in fact, you have to be very careful about the other magnitudes that may be correlating with numerosity. So in the Stoyanov and Zorzi model, for example, they try to have factorize the cumulative area in such a way that it was orthogonal to number, so that neurons cannot use cumulative area to judge numerosity. However, this introduces another correlation with item size. So item size in their data set was predictive of numerosity, was highly correlated with numerosity. The more numbers you have in your image, the smaller are on average the items in the image. So maybe the model, the deep network, is actually using item size to perform the numerosity discrimination task. So together with some colleagues, we have been trying to establish a more ecological training setup for this deep learning model by taking some naturalistic images from a machine learning, machine vision data set and segmenting them according to object detection boundaries. So now we are not actually using the real images, we are using a binary version of the images where we replace each object with a corresponding bounding box and we make it binary, white on black. And so we use this as an input for the deep learning simulations. So interestingly, as you can see, the natural data set has some distinguishing features. For example, numerosities are not evenly represented in the data distribution. Larger numbers tend to be underrepresented compared to small numbers. This is a so-called Zipfian distribution. The average cumulative area is no more constant, as in the Stoyanov and Zorzi dataset. Actually, it is slightly correlated with the numerosity. And the average per item area is still quite correlated with numerosity. So still we have some correlations with other magnitudes, but at least we are getting close to what could be the natural distribution for these quantities. Together with Jay McClelland and colleagues, we were trying to simulate the developmental trajectory of number acuity in deep networks. So on the right panel, you see the experimental data with the children, where basically you even have some infant studies probing the knowledge, the numerosity discrimination capabilities after few months in newborns. And then you can see that as you grow, so as the age goes toward 20 and 28 years old, you see a progressive sharpening of numerical acuity. So this is representing the Weber fraction. And you can see that in the deep learning model, you see something very similar. So the number acuity starts around 1.6 and then gradually becomes more and more refined. And it reaches different convergence points depending on the data set that you are using to tune your unsupervised deep learning model. So I think this is quite impressive because it shows that you indeed have a progressive gradual development of number acuity, and also that you can simulate the performance of newborns and infants with a randomly connected deep network. So this is the amount of network training. When it is 0, it means that the network is totally random. However, as a disclaimer, I should say that you still need to train the supervised classifier to simulate the numerosity comparison task. So it is not really fair to say this is a totally random model, because actually you have a random deep network, but then you are training the readout classifier with some supervision. Now, answering to the Tally's doubts and argument about the role of continuous visual magnitudes, we have been thinking about a way to extend the basic model in order to allow for a finer grained study of the contribution of continuous visual features. So we extended the architecture into something like this. We now have 2 Siamese networks, each one perceiving a different image. And in this way, we can set up a numerosity comparison task between 2 images. So we don't have a standard fixed reference number, which is like an internal numerosity, but we are directly comparing 2 visual images. And so we can also consider, for example, if the image on the right has maybe larger items or a smaller cumulative area. So we can also study congruency effects, for example. And so interestingly, we discovered that in deep networks, similarly to humans, if you have a congruent trial, so the image on the right has larger items and also larger numerosity, then you can be very accurate even if you have a random neural network and then a supervised classifier. However, in incongruent trials, especially if you are early in development, so you have a random network, you can be quite confused, and you tend to say that this has the higher number, even if in fact this is the largest numerosity, because you get confused by these non-numerical visual features. So this is already showing in some sense that also deep networks can be biased by other non-numerical visual features. However, we wanted to move one step forward, so we decided to build a new stimulus space based on the idea of De Wind and colleagues. This was a very nice paper published in Cognition by the group of Elizabeth Brannon. And basically, they were trying to build a new stimulus space where you can covary numerosity with all the other possible continuous non-numerical visual features like total perimeter, total surface area, item perimeter, coverage, sparsity. So actually field area, and then you have convex cells somewhere here. So using this three-dimensional space, you can build images like these ones that have all the same numerosity. However, in this case, you are manipulating the spacing of the items. So you are changing the sparsity or the density and the amount of field area covered by the items. Or you can keep the spacing equal, and then you play with the size. So you are changing now total perimeter, item surface area, and total surface area. So by building images like this, you can be more precise in quantifying the contribution of visual magnitudes in numerosity perception. Now, I don't have time to go really into the details of this stimulus space, but the idea is that you can model the behavioral responses by considering, besides numerosity, also these size and spacing dimensions. So you can try to factorize the contribution of size dimensions and spacing dimensions by using generalized linear models. So you will obtain three different beta coefficients, each one indicating how strong a certain direction in the stimulus space is in shaping your behavior, your behavioral response. And so we have done the same, and we have been comparing human psychophysical measures with deep networks trained and tested using the same images. So this is the power of deep learning. You can use exactly the same stimuli for testing humans and deep networks. And what we found was quite actually interesting, because we can see a very similar match to the contribution of all the different continuous visual features to the model performance. And as the model grow more mature, so you train for longer time the deep network, it becomes more and more precise. And so the contribution of continuous magnitudes becomes less and less evident. So the more you go further than zero, the more it means that you are not influenced by these other magnitudes during your numerosity judgments. So actually, people in other research labs have been seeing in developmental studies that by using the same stimulus space, you can see a gradual increment of the beta coefficient for number during ontogenetic development and a little decrease in the other coefficients. So it seems that 4-year-old children can still rely on numerosity, but they are quite confused also by, especially by spacing, like convex cell. However, as they grow, they become better and better in disentangling numerosity from the other visual features. And the same holds for deep networks. So here I plot the developmental change in the coefficients, actually beta number, beta size, and beta spacing for humans and for deep networks. And you can see a quite nice match. However, still somebody can say, well, you are always training a supervised classifier on top of the deep network. So is it true that the deep network is learning in a totally unsupervised way, but then you are always stacking a readout module to simulate the comparison task? So how much is this driven by the supervised classifier? So in another set of analysis, we simply got rid of this classifier and we focused on the internal representations developing after unsupervised deep learning using representational similarity analysis. So this is a well-known technique in neuroscience where basically you try to establish the internal similarity of different stimuli in order to discover if there are some categories that are clustered together in the internal space. And so these are the representational dissimilarity matrices for the young neural network and for the mature neural network that was trained for a longer period. And we compared these matrices with some categorical matrices representing the numerosity feature or the total surface area or the item surface area, convex hull, and so forth. And so we can correlate these different matrices with the model matrices in order to establish which is the most similar and which is mostly represented in the internal representations of the deep network. And what we found is that actually numerosity seems to be well represented in the internal representations of the deep network, even without considering the supervised classifier, but also total perimeter or convex hull or other continuous features are also factorized and represented in the hidden activations of the model. So this suggests that there is some spontaneous representation of numerosity, but also of other non-numerical magnitudes, which makes sense because they are all factors of variation in the data distribution. So let me just mention other recent deep learning work trying to tackle this problem from a computational perspective. From a more machine learning perspective, there have been some deep learning working. What they say counting is not actually counting, because in the cognitive science psychological literature, counting means that you are establishing the exact number. However, it was actually in Montreal, close to your university, that people established some convolutional deep networks to estimate the number of objects in images.
Alberto, before you present this, could I just ask one little incidental thing? What was the motivation for disentangling the supervised and the unsupervised component? It seems like there's something pejorative about an outcome that's based on a supervised component. Why is that?
Thanks for asking, because maybe I was not clear enough. So basically, I was a bit surprised that you can simulate, you can reach a pretty low Weber fraction. Let me go back just a second here. So if you look at these graphs, you may say that even random neural networks can represent numerosity because their Weber fraction is remarkable. It's not random, the behavior is quite precise in discriminating numerosities. And so a conclusion could be that even without training, you can have some numerical competence, let's say. However, as I wrote here, you always need a supervised readout to ask the model to exhibit some behavior, some behavioral response. And so this is making a bit of confusion. It's not clear whether that performance is due to some high quality representations built here or to this extended supervised training. So even if with the random representations you can do some numerosity estimation, is it really necessary that you are developing numerical knowledge in an unsupervised way? So this was the question that we tried to answer. What happens if you don't consider this module and you just analyze the representations emerging from unsupervised learning? So of course, if you have a random connectivity here, you won't find any correlation with these different categorical matrices.
I understand that, but it's still a question. After all, unsupervised training is training. It's learning. It's not random. You've changed the configuration already. Why is that not enough? And why is it necessary? Sorry, the other way around. Why is it positive or negative if it turns out that unsupervised training can or cannot achieve the outcome?
Okay, now I see your question. Okay, so I think that was one of the open questions that I had in the next slide. So let me hold on a second. After this slide, I have a wrap-up slide pointing out to these questions, which I think is interesting. So we have been trying, following this idea that Stefan just mentioned, to see if we can build a more powerful generative model that is able to fully disentangle numerosity. So we say, okay, let's try with the InfoGAN, which are a very powerful unsupervised deep learning technique, to try to learn factorized representations of the data distribution. So maybe an InfoGAN will be able to fully disentangle numerosity and to generate images with a controlled number of items. But that was not possible. So that was a partial failure. And so we were wondering why. So apparently you need some supervision in order to fully disentangle numerosity. Other people have been doing some work with other deep learning architectures. This is a new RIPS paper published last year. People at Caltech have also been recently trying to see if you can notice a number sense emerging in a less constrained scenario, where basically you have an agent trying to understand what could have been the action causing an image to change into another one with a different number of objects, like picking up an object or placing an object in the scene. So in line with a more embodied cognition perspective, let's say. And finally, still in Science Advances, they have been recently publishing a paper where it seems that they can find a visual number sense in untrained deep networks, so totally random deep networks. So again, I think all these investigations may have some methodological weaknesses because they were not carefully testing the contribution of all possible continuous magnitudes. So I think we should be prudent. However, you can see that there is a bunch of new research directions that have been explored. We have also been trying to extend this to sequential stimuli. So I mentioned this last time because I remember Tali was raising the point of sequential numerical processing. So together with Serena Dolfi, a PhD student in our lab, we have been trying to extend the stimulus space of the wind and collaborators into something that could be presented sequentially to the subjects. So you still have the numerosity axis, but now you have duration rather than size and tempo rather than spacing. And so tempo is encoding the total stimulus duration and also the mean event period, so the average length of stimulation. In the duration, instead, you have the individual event duration and the total event duration. So basically, we are trying to translate this spatial domain into something that can be studied sequentially to see if also in this case we can disentangle the contribution of numerosity from that of other continuous magnitudes. So the take-home messages so far is that empirical and modeling studies support the idea that numerosity is a salient feature of our visual environment. However, it might not be innate, as some people were proposing some years ago. It can be processed by neural networks with random connections, which is remarkable and suggests that maybe you just need some processing architecture with some basic processing capabilities to estimate numerosity. And also it becomes gradually refined following unsupervised deep learning. However, also its processing may be intertwined with that of other magnitudes. So the responses of the model, as in humans, are modulated by continuous visual features. Other magnitudes like density, total area are spontaneously represented in the deep network. And finally, feedback is required to focus on numerosity. So this is related to your question, Stephen. Basically, you need to calibrate and give feedback in experimental tasks with humans, and with deep networks, you need to stack a supervised classifier on top of the deep network. So it's still an open question whether you can really fully disentangle representations of pure numerosity in a totally unsupervised way. So I think it would be nice if this could have been possible, because it suggests that you don't need supervision to discover the concepts of numerosity, at least approximate numerosity. However, to my knowledge, this wasn't yet demonstrated. If so if we can build a very complicated, deep generative model that can fully disentangle numerosity, would such model be able to generalize, for example, by producing previously unseen numerosities? So one of the research goals that we are pursuing in these months is to try to interpolate and extrapolate numerosities that were presented to deep networks. So you show, for example, now only even numbers or only odd numbers, and you see if the network can spontaneously generate something in the between by doing some exploration on the internal representations, like you find the direction where you can move in the internal space in order to generate the missing numerosities. And this may even be extended to extrapolation tasks. So you train a model, a generative model, from numerosities from 1 to 20, and you try to generate 25, 30 items. So I think this is quite challenging. And again, to my knowledge, no deep learning model has been shown able to succeed in this kind of tasks. And another interesting question is there a computational bottleneck that allows humans to accurately track only numbers smaller than 5? So why is that number 5, the magic number 5? What could be the reason for this limit? Is this something intrinsically related to the number of neurons in our visual cortex, for example? So can we show that a deep network under some representational constraints will also be suffering from such a representational bottleneck? So I think these are all open questions, very challenging, but also accessible in future studies. So I encourage you to pursue these open questions if you're interested in the topic. So, Stefan, did this answer your question?
Not only did it answer my question, but it exceeded all of my expectations. That was a wonderful talk. I
didn't finish it.
Okay. My expectations are too limited. Go ahead.
Let me, I think in 10 minutes I can. So I have now the most challenging question. It is, how can we move now from approximate to exact numbers? So I think this is the key question. And this is the challenge ahead. So if you're interested, you can read these nice little summary papers by Rafael Nunes, published in TICS a couple of years ago. So basically, we know that quantical abilities, so approximate, let's say, abilities, are shared with many animals, and they are non-symbolic. So you can discriminate quantities, you can do subitizing, so we can exactly estimate numbers up to 4, maybe 5. However, at some point, humans have been able to also deploy, for example, language, natural quantifiers, to establish more concrete symbolic concepts. And actually, at some point, humans with explicit training and enculturation have been able to develop even more abstract and sophisticated numerical abilities, those allowing for exact quantification. So we have been introducing written systems of numerals. We have been starting with non-positional systems like the Roman numbers, and then we move to the Arabic numbers that allows to encode the number positionally and create a combinatorics for numerical concepts. And then we have been able to further extend this to, for example, transfinite numbers, complex numbers. So the power of math is really keep on moving and pushing the frontiers of our knowledge. So how is it possible that we have been able to do this? So I think this is the new Holy Grail for connectionist models. So if connectionism eradicated, at least partially, the linguistic assumption that language is based on symbolic structures manipulated according to logical or syntactic rules, well, the next challenge, I think, will be to move into the realm of mathematics. This is a much more structured domain compared to natural language. And there is no doubt now that we are dealing with the real symbols. So if I show you something like this, there's no question that these are abstract entities, totally abstract entities that could be manipulated according to syntactic rules. So recently, people in big AI companies have been trying to tackle these challenges. So this paper was published a couple of years ago by people at Google DeepMind and collaborators. So they noticed first that deep networks cannot generalize knowledge of integers outside the range of numerical values encountered during training. So this is related to the extrapolation task that I discussed a few minutes ago. So you can try so many different activation functions for your deep network, but if you train it only within this range, and then you ask it to produce larger or smaller quantities, it will totally fail. So the absolute error will grow as you move further away from the training range. So they have been proposing these neural arithmetic logic units where linear activation functions are further manipulated within the network using some primitive arithmetic operators. However, I consider this as cheating because you are building numerical knowledge inside the model. This is hardwired, okay? However, the result was interesting. So they have been testing their model on this MNIST digit addition task. So this is a totally symbolic addition task. And you are provided with some images of numbers and you have to sum them and produce an integer, a real value as output. And so beside these neural arithmetic logic units, they also have this neural accumulator, which is a similar architecture that was able to be more successful than other popular models, at least in the digit addition task and also in some counting tasks. In another task that is called language to number translation, the training set consists of the numbers between 0 and 20, in addition to some random samples from the rest of an interval, going up to 1,000, I think. And so you have been presented with some natural language number words, 334, and the neural network has to produce the corresponding quantity. So you see 3 is then transformed into this quantity after 300, and 30, so 334. So you see that by the end, the deep network is able to accurately produce the correct activation corresponding to the number word. So this was also interesting and exciting, I think. In this case, the neural arithmetic logic unit was performing better. However, as I said, some algebra was built into the model, which I think it's a bit tricky and it's cheating a little bit. And people in Facebook AI research have also been doing something similar, deep learning for symbolic mathematics. They have been training deep networks to perform symbolic integration and even solution of ordinary differential equations. They built a specific syntax for representing mathematical problems, like in a tree-like representation. So you can represent this formula using a tree-like structure like this, which is much easier to parse for a deep network. And they were able also to generate a huge data set for training these advanced sequence-to-sequence architectures. And the results are surprising and quite impressive. So deep networks outperformed commercial computer algebra systems like Mathematica or MATLAB in this kind of problems. So you have an equation quite complex, and they found the solution, the exact solution. So I think this is impressive because this is really symbolic math. However, it is succeed possibly without any knowledge of the underlying semantics. So this is quite interesting. And I just point out to some recent discussions online about how close we are to building machines that can do automatic mathematical reasoning. And Microsoft even launched the International Mathematical Olympiad Grand Challenge to build AI systems that can win a gold medal in the competition. So my question is, are we really close to this level of mathematical skills in machines, or maybe this is still something that needs to be better studied? So even GPT-3, which is very popular nowadays, can show some systematicity. For example, you can ask GPT, when counting what numbers comes before 100, it will say 99, correct. And what before 123, 122, great. Even going up to 1,000, it really has captured the syntax for generating number words. However, if you keep on increasing this, and you go, for example, to millions, it will say that 900,099 comes before a million, which is wrong. But just even before 10,000, the answer was not correct. So you can see that these kind of errors show that there's no really understanding of the underlying numerical semantics. So I will conclude by just following up some recent proposals by people in DeepMind interested in this kind of symbolic behavior in modern AI systems. Basically, the idea is that symbols are entities whose meaning is established by some convention. And this has some maybe developmental ontogeny. So we learn to use symbols. We don't need to build in some symbolic abilities. And so the ability to exhibit symbolic behavior may be emerging gradually based on experience, maturation, and formal education. And AI research should explore social and cultural engagement as tools to develop the cognitive machinery necessary for symbolic behavior to emerge. And I think there are great examples in the mathematical cognition literature. When children are learning to process symbolic numbers, you can see that they may make some mistakes or misunderstandings because they are confusing symbols with more embodied representational systems. Okay, so I think this is a nice example. And I have an even more interesting example. I need my audio for this. So let me unplug my headphones. So in Southeast Asia, for example, they teach children how to use mental abacus to perform more accurate symbolic manipulations. And these children, you can see 6, 7 years old children, have extraordinary numerical skills, symbolic numerical skills. For example, they can sum digits with a very accurate and fast processing.
Two-digit 10 numbers ready. 54, 39, 38, 94, 28, 12, 10, 67, 50, 67. Answer.
459. 459.
And then we can even move to older children, so 9 to 12 years old.
4-digit 10 numbers ready. 2,110, 1,652, 5,159, 4,981, 7,465, 5,825, 2,197, 6,552, 1,891, 9,716. Answer.
47548. 47548. 47548.
Okay, so I will conclude by just showing you my last slide that is trying to propose a research direction for the role of embodiment and external representational media for building more cognitive deep learning models. So my hypothesis is that a machine, a deep network, could learn symbolic mathematics if equipped with proper learning mechanisms. So we need a way to mature and extract knowledge from the sensory environment. However, it should also be immersed in a proper cultural and educational environment. So it will need to be able to manipulate some external representational media like linguistic number words, finger, in your hands, tally marks, even a mental abacus, maybe a physical abacus and then a mental abacus, in order to more efficiently process numerical information. And this is evident even if I simply ask you to estimate the number of items in this image. It's quite challenging, but if you put them into a different configuration, for example, into a dice configuration or into a fingers configuration, it's much easier for you to groupize and give a precise estimate of this number here. So I really think that we need to move from passive machines that learns by just observing the environment to more active, interactive machines that can learn to manipulate the environment to their advantage, to build more accurate representations of the information. And this may lead to, finally, symbolic behavior and symbolic competence. So I just want to thank you for your attention and thank Marco Zorzi and Jade McLennan, who has been very important sources of inspiration for studying these topics.
Okay, let me now repeat my premature thank yous. Could you remove your sharing the screen
Sure.
so that we can see the people? I'm sure there will be questions. I repeat again, it was an excellent talk, and I leave it open now for people to ask questions. I don't want to dominate this.